Yeah.
Alrighty, it looks like we are ready to go.
Yeah.
So thank you, everybody, and welcome to this week's SEDS online webinar. As always, we'd like to thank our sponsors from IAS, which allow us to offer all of these resources completely free of charge. So this includes things like our recorded lectures, our learning tools, and even virtual field trips. So make sure you're always checking the website to see all the new info we have. Today's lecture is by Dr. Yudong Sun, who is a paleogeochemist at the University of Erlangen-Nuremberg. Dr. Sun got his PhD degree from China University of Geoscience and University of Leeds. And his research interests include using multi-proxy analyses to understand the Permo-Triassic crisis and its aftermath in order to better understand the driving mechanisms and ecological responses to these mass extinction events. So thank you so much for coming to today's talk, and I'll give you the floor.
Yeah, pleasure is mine. Thank you. So I will share my screen. Okay, so first of all, thank you for inviting me here. So my name is Yadong. I'm currently working in Erlangen. And today my talk is focused on the nitrogen cycle and the Ammonium Ocean hypothesis for the end-Permian mass extinction. Because the nitrogen cycle is a rather complex biochemical cycle, I hope I can explain it clearly and you enjoy. If you feel confused somehow, please don't worry, because I confuse myself all the time. Okay, so first of all, we look back into the time. So the general climatic conditions of the Paleozoic Mesozoic transition is like this. So basically, the Permian is generally considered a glacial time. The big glacial ends somewhere in the Indo-Capitanian, and the Triassic, the entire Triassic is considered a warm house, and the early Triassic is a hothouse climate for 5 million years time. And the early Jurassic is probably generally cool, but it's very controversial because the temperature record at that time was mainly done on belemnite. If it's a surface dwelling, it's not yet resolved. So during this time, there are 3 major mass extinctions. One happens in the somewhere in mid-Permian called Capitanian mass extinction. The largest one is the Permo-Triassic one. Of course, the other big 5 is the TJ extinctions. At the same time, there are additional OAEs, Oceanic events. These 3 major extinctions come with OAEs, but additionally, there are Smith Pass extinction, Mesocarnian, Carnian, Pluvial event, and the Tuarcian OAEs. And these 2 are in the classic Wignall and Halleman-Wignall extinction book. So the end-Permian mass extinction profoundly impacted the ecosystem, the structural ecosystem. The extinction itself basically wiped out 95% of marine life and about 75% on land, and resulted in a completely collapse of Paleozoic ecosystem. But the recovery in early Triassic comes is accompanied with this very large carbon isotope dispersion, as it took also a really long time. So there are very interesting gaps in the aftermath of the end-Permian extinction. Is include no coals on land, no corals, no chert in shallow platform, no Amazonian reefs, and the microbialites are extremely abundant compared to other times. And the seawater is also quite unique. It was a carbonate oversaturated. The seawater is generally anoxic, characterized by low sulfate concentration. And today we will focus on this Ammonium Ocean part. Of course, the trigger of this extinction is considered as because of the eruptions of Siberia traps, the mother of all volcanoes. Some say it's the largest in the Earth's history, but others say, oh, the canopy in the TJ is the largest. It's the one of the largest. So, but understanding the killing mechanism of the Permo-Triassic extinction is very important, because anoxia is one of it. And but how anoxia establishes is kind of controversial. But the general hypothesis involves this mechanism. So first we have eruption of the subaerial traps. It increases the carbon dioxide concentration in air and the atmosphere. So this leads to 8 to 10 degrees warming, and warming enhance weathering. Weathering bring more nutrients, and more nutrients lead to high productivity ocean, and this lead to anoxia, and anoxia lead to mass extinction. Of course, because the warming is so significant in the Permian-Triassic, it also can kill things directly. And this hypothesis is become a classic and widely implicated in many past extinctions, or some call it a eutrophication hypothesis. But there are missing link in this hypothesis, because if you look through this chart, and there is a question mark here. So it has weathering increasing nutrient influx, and the nutrient influx lead to high productivity. You may ask, oh, really? Then what nutrients? The question is, what nutrients can weathering bring, and what are the phytoplankton needs? So the nutrients in general is basically very well summarized by in the red field ratio. Basically, a red field found in marine phytoplankton, the carbon, nitrogen, phosphorus ratio is about 100 to 6 to 16 to 1. Basically, it's a decrease 1 order each. And later that the extended red field ratio, it includes all sort of trace metals, which are essential for photosynthesis. And weathering actually bringing mainly phosphorus, plus some trace metal, but not nitrogen. And the basic hypothesis of this PT eutrophication hypothesis is that phosphate controlled productivity. In fact, phosphate limitation is not always the case, especially when we consider the PT ocean is anoxia. In anoxic conditions, phosphate recycle is always occurring, and it's release partially the fixed phosphate into the water column. So as an example, if you look at the modern days, the Southern Ocean, we have these large areas. We have a very high nutrient concentration, but a low productivity. And the reason of this is more complicated, but to just give you an example that the high nutrient not necessarily means high productivity. So for the marine nitrogen cycle, so it's largely independent from terrestrial input, and the input is actually relying on nitrogen fixation. Basically, you get atmosphere nitrogen gas into through exchange to seawater. It's fixed into ammonium and ammonia. The removal of fixed nitrogen in the ocean is rely on this process called denitrification. Basically, nitrate and nitrite become a nitrogen gas. And both ammonium and the nitrate, these can be uptaken by organism and become organic bonded nitrogen. Of course, there's a transform which oxidize ammonium into the nitrate and nitrite. And microbials plays a very important role in almost it's a critical role in ocean nitrogen cycle, because the nitrogen fixers, they are exclusive prokaryotes, and they prefer anoxic conditions, and ammonium oxide bacteria and archaea are light sensitive. Basically, this reaction is light sensitive. And there are already studies on the nitrogen cycle in the PT, and these formed a classical theory, and this argued against the eutrophication hypothesis. This called nitrogen limitation lead to low productivity. It works like this. Basically, the nitrogen isotope decrease from very positive values from 10 to 0 in multiple places. This can only work when you remove a lot of nitrate from the water column, because when you measure this side, the isotopic composition is around 0. When you measure this side, the isotopic composition of nitrogen is about 5. When you have a lot of denitrification, this value become enriched. You have values of greater than 5. This basically showing a denitrification process. And the theory includes the intensification of ocean stratification. So basically, they explain the draining, the depletion of nitrate is because for example, the weakening of upwelling because it all becomes because of the nutrient trap, and the nitrate cannot be moved to the euphotic zone. And this hypothesis is not wrong, but also not completely correct, because I will explain in these 2 slides. Because there's the first key hypothesis is first the nitrate was the most important nutrient in the ocean. This is both correct and incorrect because you have to think about what likes nitrate is basically diatoms, large algae, and seagrasses. And what about most phytoplankton? They actually like ammonium over the nitrate, because the nitrogen in ammonium is in -1 charges, and in nitrate is +5. So there is a redundant energy cost to reduce this to reduce nitrate into ammonium, because in ammo acid, this nitrogen is more close to ammonium in thermal charges. And for the Permo-Triassic cases, the primary producer changes. In the late Permian, there's a lot of benthic calcareous algae plus phytoplankton. But during the extinction, all the calcareous algae died out. So the primary producer in early Triassic is basically almost purely phytoplankton. And the second problem, this classic theory is there are nitrate in deeper reservoirs. For example, they are trapped in nutrient trap. This is correct in modern settings. This is correct in many oxygenated settings, but not absolutely correct in the PT settings. You have to first understand why it's nitrate occurred in the deep, because the nitrate production is always rely on nitrification, which is this blue arrow. You oxidize ammonium into nitrate, and this happens below the euphotic zone because the bacteria and the archaea carry out this function, do not like light. So all the nitrate production can concentrate in the deep and dark water. And so one may ask, okay, how about nitrate shuttle? Because this mechanism doesn't work in pre-Jurassic oceans because there's no diatom. In modern oceans, the diatom basically sinking into deep water and they carry up the nitrate into the euphotic zone and during the day. So this mechanism not existing for the Permo-Triassic. So in order to resolve these problems, we established this Ammonium Ocean hypothesis. Before I explain this further, so there are some basic facts. First, the nitrogen cycle is biologically mediated. So basically, it follows the rule of energy. Which gives more energy, it goes first. And the second is nitrogen reaction is always, many of them are redox sensitive, but not in a simple way. And the third is the residence time of nitrogen nutrient in the ocean is very short, so you can have very large changes over a short amount of time. So it's basically a very good tracker for the past crisis. So if we look at this chart, so this is the Gibbs free energy. It basically tells you how much energy yields of each of these reactions. You can see when there is oxygen, the energy yield is the highest. When there's no oxygen, the first priority is nitrate. So it's a yield almost similar energy, and it always goes down. When there is, for example, sulfate, it's basically cannot, it's yield so less energy, it cannot compare to these two. So in case of anoxia happens, the nitrate must be gone first because it's yield so much energy. So if you remember in the second slide, I said the PD ocean is anoxic and has a low sulfate concentration. When we think about anoxia, you always think of what causes the oxygen in the water column, because respiration is a way, it's a way of intercellular energy extraction, and it oxidizes, for example, glucose into carbon dioxide. So there's a great changes during this process. Basically, the carbon lost all the electrons, so the carbon become 4+ charges. So the electron acceptor in order is basically the oxygen, nitrate, manganese, or iron oxide. The last is sulfate. If the sulfate is already low because it's being used to oxidize, for example, organic matter, that must mean all these are gone. So these are called redox lattice. So we basically divided the entire nitrogen cycle by redox conditions, and subdivided into ideal situations. For example, in fully oxygenated ocean, so we removed all the anoxic reactions. So you see there's a strong nitrification. So this shift this ocean into a more nitrate dominated ocean. But in anoxic ocean, but with enough iron supply, and you see the anoxic reaction kicks in. It's all the arrows are pointing away from this nitrate end. So eventually the nitrate will be depleted, and this lead to nitrogen cycle only has the half cycle. Basically, the nitrogen gas was fixed into ammonium. This was uptake by organism into organic matters. And in the worst case scenario, for example, in fully euthenic conditions, all the trace metals was removed from water column, and there's no way to fix nitrogen. Basically, the entire ocean was dead because of the lack of nitrogen fixation. Then this lead to internal cycling between the ammonia to organic matter. This will lead. This will generate less and less nitrogen nutrient in the water column. And this model can be a really easy test in modern day Black Sea, because the Black Sea is highly stratified. It has oceanic waters down there. If you watch the profile Black Sea ocean, you can see in the oxic part, which correlate to this model, and the nitrate is very high. But in the suboxic level, when the denitrification comes, which is this, so you have an increased number, the increased amount of nitrogen gases, because the nitrate was decreasing and transferred to nitrogen gases. And below the suboxic to anoxic boundary, the ammonium concentration increases. So we can also test this in the field with data. So basically, we test this in two locations. One is in South China, one is in Spitsbergen, and the oceanography is very, very different, because in the well circulated ocean, so everything is fine. You have a deeper nutrients bring up by upwelling and by current, and very well mixed. But by the in the early Triassic cases, you have microbial developed on the coast, and all the anoxic reactions happening here. Then the thermoclines deepening and making the nutrient traps. So if we look at the nitrogen isotope data, we all across the permatriassic boundary, there's a there's a minor difference when this denitrification happens, but coming into the early Triassic, it all goes from plus values to values around 0, which is indicating a strong nitrogen fixation. And in some cases, it shows very negative values to -3. This only happens when the organic matters are coming, has the nitrogen source from ammonium, which means that there are ammonium in the ocean. And there's no nitrate signature in the equatorial oceans. And the nitrogen isotope basically represent low-cost signatures unless this event is truly global. If we look at all the most of the nitrogen isotope data published, you see the denitrification always coming around the Permian-Triassic boundary interval, and slowly goes into the early Triassic is all around 0. And become a nitrogen fixation dominated scenario. So this summarize this flow chart summarize. They say in normal ocean, before the anoxic and the extinction kicks in, we have a nitrate ocean, and the nitrate slowly become depleted, and we go into a nitrate starving ocean. This further evolved into the ammonium ocean. And please note, when I said the ammonium ocean, which means the ammonium is the dominant nitrogen nutrient in the water column. It not necessarily means it must have higher concentrations, but when it comes in high concentrations, it will lead to microbial blooms and ammonium intoxication. But I will show it in the later 2 slides. And the interesting thing is that the ocean nutrient structure changes because there's a decrease in efficiency in energy extraction. So ammonium toxicity kicks in when we have a high amount of ammonium in the system. It can be used as a herbicide, says Google. And but it only works in higher plants. Actually, the lower plants and the phytoplankton, they love ammonium better. But here I show a photo of aquarium. I can tell that these fishes will be dead in like about 1 to 2 weeks time. But the question is, what killed the fish? You may say, oh, anoxic, because they don't have enough oxygen. But actually, that's not true, because there's so many algae, there are tons, there's enough light, there's tons of photosynthesis going on. But the real killing mechanism is the build up ammonium in this tank. And what can we do if we have this situation? Basically, you can follow this rule of nitrogen cycle, and you have to transform the ammonium into nitrate, because the nitrate is almost not harmful to higher animals. And in order to do this, because this reaction is light sensitive, you just need to kill the light, and probably adding in a water filter to get rid of some of these algae. And how the ammonium toxicity basically attacks the higher animal in their central neural system, as it's amplified in seawater concentration, because the ammonium can become ammonia in higher pH, and these have higher permeabilities into the cells. And this killing mechanism is very obvious in fish farming industry. Also, there are it's a very strange thing. It's also plays a role. We think it played a role in selectivity in ammonoid extinction, because some ammonoid have so high concentration of ammonium in their tissues, because they use it as a mechanism for buoyancy, and they tend to survive. But some don't have. When you have higher ammonium, basically you can kill them. And the second, we talk about the nitrogen loss, because because of the anoxic conditions, there's always nitrate is gone, become a non-nutritious species. Otherwise it's become ammonium, or it's just simply gone. When this ammonium, there's another example. For example, in Texas, there's a brown tide kicks in from time to time. This is also because the human sewage brings a lot of nitrogen nutrient. Then there's a question always say, oh, you can counter argue with, for example, the upwelling zoo in Peru. There's enough nitrogen nutrients coming up, but the Peru has basically an oxygenated water column here. So there's always nitrate production in deeper ocean. In the Permian-Triassic, it's a different scenario. Okay, so here I can come to my conclusion. First, your eutrophication scenario should be at least reconsidered for some extinctions. It's not universal. And especially for the PT, because PT, the early Triassic has very low, there's no source rocks, they have very low TOC rocks than the Permian. And for the, let's say for the Gulf of Mexico, you have enough nutrients, enough nitrogen, you have a very different scenario. The second is Ammonium Ocean can lead to locally high productivity and microbial blooms. And for the cyanobacteria, because some of the cyanobacteria, they have the ability to fix the nitrogen from the air. So this gives them a competition leverage to outcompete other bacteria and lower plants. But the third conclusion is generally productivity should be low because the loss of nitrogen, and probably except for some coast areas, you might still find the high productivity places. Okay, so I will end my talk here, and thank you very much.
All right, thank you very much. That was very interesting.
Yeah.
So the chat is now open. So if anybody has a question, please type it into the chat, and don't forget to send it to everybody and mention where you're watching from and your name. So while we're waiting for messages, I'll just ask one.
Yeah.
So you mentioned that this works in particularly well for the Permian-Triassic. Have you seen similar evidence for any other mass extinction events?
Yes, there are. Because this hypothesis was not established before, and I think in Toasin there is, but it's not globally, because in Toasin, for example, in the Jickens paper, he reports very low nitrogen isotope numbers, like -4-ish. This is very rare in reality. Only if this only occurs because when you fix the nitrogen is from the air. Only cyanobacteria fix it. The air has a nitrogen isotope ratio of 0, and this come into your organic matters. And it recycles in the seawater. If you want it to become even more depleted, you either change the enzyme, for example, remove all the iron species in the seawater, or you recycle the ammonium, so you get these very negative values. And I think there's another paper recently for the Cretaceous OAEs. They also thinking that direction, but this Ammonium Ocean hypothesis, this model was new, so I think still need some time for people to think about it, about application. Yeah,
that'd be very cool to go back and see if we can reinterpret some things.
Yeah, the unfortunate thing is because the nitrogen isotope is always, because I also worked with colleagues on Toasin. In some places you don't see it, because if you must have a global anoxia to get a global signal. If you have a local, very strong anoxic, you found the ammonium signature in that place. If you go to a place which is more or less oxic, you don't find it. I think it makes sense because it's also a very valuable source. If you have a large amount of it, so all the phytoplankton will just jump in, and they will consume the ammonium until other nutrient limit. For example, it consumes all the phosphate. So it's neither way. The high productivity can only last for a while unless the nutrient is continuously supplied.
Yeah,
what
okay.
I think.
Yeah. So our next question is from Stephen in Derby.
Yeah.
This is from a non-geochemist.
Yeah.
So sorry if you missed this.
Yeah.
What effect, if any, will anthropogenically driven ocean acidification have on this process?
Well, oh, that's a very good question. Let me think about it. Well, pH. The question is, I would guess that, well, pH changed the nitrogen cycle significantly. I would think if the pH change very minorly, it won't have very obvious impact yet. Yeah, to my understanding, because it's the nitrogen cycle is more redox controlled and the light controlled, and yeah, basically these two things control the nitrogen cycle.
Okay.
I wouldn't I think not very significant impact will occur.
All right, so if anyone else has some more questions, please put them in the chat. But I have another question.
Yeah.
So you showed how there was two different scenarios where you had like a well-mixed ocean and a stratified ocean.
Yeah.
For the well-mixed one, how does the light affect that then? Because it would be relatively within the photic zone.
Yeah. So let's see. So basically, in well-mixed ocean, basically like here, so let's say in some cases you develop the oxygen minimum zone along the coast. So basically, you still produce, and nevertheless you oxidize ammonium below the euphotic zone. So this must happen. Let's say not must, but it's overwhelmingly produced down there. If you think about this part, the euphotic zone, they also can transfer, for example, the ammonium into nitrate in the night, but it's not enough time, and they won't accumulate because during the day, and nitrate is such a valuable energy, so just all the phytoplankton just jumped in. So this light control on the ocean stratification only affects the thickness of the euphotic zone. In this stratified ocean, even let's say if this here is not anoxic, they still can produce here. Then there's a problem is bringing up nitrate into the surface to the euphotic zone for photosynthesis. So you end up have a lot of nutrients down there, but not much can be used for photosynthesis. That's the problem. Also, when especially for the early Triassic case, it's so warm, so there's a on top density barrier, so it makes the seawater vertical mixing even harder.
All right, very interesting. All right, our next question is from Teresa from Vienna. Thank you for this very interesting presentation of a difficult topic. You mentioned that the rise of diatoms changed transport mechanisms of nitrogen. Could you explain again how this impacts the nitrogen cycle? Yeah,
of course. Because the diatom, I liked, although I don't work on diatom is an amazing thing. because it's so special. It is a phytoplankton. It uses both. It uses basically the nitrate. Actually, this only nitrate is only preferred by higher plants because let's say after the Cretaceous, for the primary producer in the ocean, there's still seagrass. Seagrass is actually plant. It's not seaweed. Seaweed is still algae, and this makes them so profound because now the ocean, there's something appear in the ocean can utilize the nitrate, and this gave them a profound leverage and to bloom. That's one aspect, and the other aspect is this floating mechanism. So basically, it occurs as we said before. This oxidizing ammonium into nitrate occurred mainly below the euphotic zone. So and the diatoms, they need these nitrate. So basically, what they do is they sink down below the euphotic zone, and they grab the nitrate, and they flow up in the euphotic zone during the day, so they can utilize this nitrate and do photosynthesis. So this is the term, the nitrate shuttle by the diatom. So it's amazing evolution. That's the two major impact. And because of this, basically you have a better circulated nitrate in Modern Ocean.
That's very cool. I didn't know diatoms did that.
Yeah.
Our next question is from Ross in Queen's University in Canada.
Yeah.
Very interesting talk, thank you. From soil chemistry, I remember ammonium is strongly absorbed by some clays, so things like smectite. Any chance of seeing actual high ammonium concentrations preserved in marine sediments?
No, at the moment, there is no way to measure it. We can only infer from nitrogen isotope from organic methods, because they utilize, for example, either this side of ammonium or this side of nitrate. And because I work in deep time, so there's no chance you can measure seawater, and they are all becoming rocks. So there's unfortunately not yet a way to measure it in the marine settings. I think maybe when people working on soft sediments, there are still some chance, but for deep time, unfortunately, no. But there is some other way to do it, because the nitrogen cycle is so logical. It follows the rule of energy, and it can be modeled. So there are colleagues in Hamburg, they basically working on PETM. They always have this ammonium edge in the ocean, which they cannot explain, and they cannot observe this in modern ocean. So basically, these things, because in the model, the oxygen minimum zone is much larger than it should be. So these, the model produced this higher ammonium in seawater. That's two ways we can find some evidence. For deep time, it's so difficult. So direct measurement, it's I'm not aware of any possibility to do it. Sorry. Yeah, but soil scientists, they are awesome. They can do everything. I'm sure they will be able to.
Yeah, maybe a field trip to the Black Sea will help.
Yeah.
Do some sampling.
Yeah.
All right. Well, thank you everybody for attending this week's webinar, and thank you again, Yudong, for your awesome talk. Next week's seminar is at its regular time at 4 p.m. UK time, when Tim Cullens will be talking about depositional processes in gravity currents. So hopefully we see you all there, and thank you again.